This lesson is all about data privacy and privacy-enhancing technologies, or PETs for short. You'll gain some intuition, learn how to think about PETs in the context of federated learning, and dive into differential privacy as an example. Let's get to it. When we look at federated learning through the lens of privacy, we can say that federated learning itself serves as a data minimization solution by preventing direct access to data. However, the model updates exchanged between clients and server can still potentially lead to privacy leaks. There are different possible attacks that need to be considered. Depending on the attack model and the adversary's role in federated learning, various privacy attacks can be constructed. The adversary can be the client, it can be the server, or it can be a third party. Let's look at 3 examples. A membership inference attack aims to infer the participation of data samples. An attribute inference attack aims at inferring unseen attributes of the training data. And a reconstruction attack aims to infer specific training data samples. For example, researchers have shown in a paper how, in one particular setting, a malicious server was able to reconstruct training data samples of a specific client in federated learning. You can see that the reconstructed images are not the exact same images, but also that the quality of reconstructed images is surprisingly close to the original data. Differential privacy is a prominent solution to enhance privacy for individuals during a data analysis. It obscures individual data by adding calibrated noise to query results, which ensures that the presence or absence of any single data point does not significantly impact the outcome of the analysis. This ensures accurate analysis without compromising sensitive information. So let's say you have 2 datasets, D and DR, that differ in only one data point, Alice in this example. Differential privacy guarantees that any analysis M, like calculating the average income for example, will produce nearly identical results for both datasets. O and O' would be similar in this case. Differential privacy in machine learning would provide us with the guarantee that if we train a model M1 on dataset D and then add or remove a data point, such as Alice's data in this example, and we train a second model M2, the resulting models M1 and M2 will be indistinguishable to a certain degree. This degree of indistinguishability is quantified by the level of privacy protection we aim to achieve. When we look at differential privacy, or DP for short, in the context of federated learning, we see that it can be applied at various stages of the process, including during model training, aggregation of model updates, and communication between clients and the server. Depending on its application, DP provides us with different levels of privacy. In this lesson, you will learn about 2 variants of differential privacy: central DP and local DP. There are 2 important topics regarding DP. One is clipping, which bounds the sensitivity and mitigates the impact of outliers. Sensitivity in this context means the maximum amount that the output can change when a single data point is added or removed from the dataset. And the other topic is noising, which adds calibrated noise to make the output statistically indistinguishable. In central differential privacy, the central server is responsible for adding noise to the globally aggregated parameters. It should be noted that trust in the server is required. The overall approach is to clip the model updates sent by the clients and then add some amount of noise to the aggregated model. In local differential privacy, each client is responsible for performing DP. Local DP avoids the need for a fully trusted aggregator. Each client is responsible for performing clipping and noising locally before sending the updated model to the server. Let's jump into the lab. As usual, we start by importing utility functions and classes. We also import both a server-side differential privacy strategy called differential privacy client-side adaptive clipping and a client-side adaptive clipping mod called adaptive clipping_mod. We'll go into what these components do in a minute. Like in the previous lesson, we load the MNIST dataset and partition it into 10 parts using Flower datasets. We also define the Flower client like in previous lessons. We define the client_fn function that initializes train loader, test loader, and Flower client. When defining the client app, we use a new feature called Flower mods. Mods, also known as modifiers, allow you to perform operations before and after a task is processed in the client app. You can use built-in mods or even define your own custom mods. Here, you use the adaptive clipping mod that performs the adaptive clipping of model updates before sending them back to the server. On the server side, you start by creating the federated averaging strategy as usual. This time, we'll give it a different name. We'll call it Fed Averaging without DP. Instead of passing our federated averaging strategy object directly to server app, wrap the strategy in a wrapper strategy called differential privacy client-side adaptive clipping. To do that, you create an instance of differential privacy client-side adaptive clipping and you pass it the previously created strategy object along with two DP-specific arguments, the noise multiplier and the number of sampled clients. The differential privacy client-side adaptive clipping strategy wrapper is a strategy itself. It wraps other strategies and is responsible for applying DP on the server side. This means it receives model updates, it forwards them to the inner strategy for aggregation, and then adds noise to the aggregated model. The last step is to create server app as usual. You now have a matching server app and client app that can perform central DP with client-side adaptive clipping. Let's run it. You now have a matching server app and client app that together can perform central DP with client-side adaptive clipping. With both our server-side DP strategy and our client-side clipping mod configured, we can see how the federated training runs with DP. After the local training, a client-side mod clips the parameters and sends the clipped model updates to the server. The inner strategy then aggregates those model updates and the DP wrapper strategy adds noise to the aggregated model. You can run this experiment as usual via run simulation. This time you run the simulation with 10 simulated clients and you select 6 of those clients in every single round. This is what fraction fit equals 0.6 results in. The logs are a bit more noisy now, but what you can see is that on the client side, the mod clips the parameters. You can see some logs starting with adaptive clipping _mods, and it says parameters are clipped by a certain value. You can see that in some of the logs that start with aggregate _fit, central DP noise with a certain standard deviation is added. Because of the clipping and noising, DP often leads to slower convergence. This is why for this experiment we use a small noise multiplier, which results in less privacy, and we run the federated training for 50 rounds, and preferably more with regard to this desired privacy and utility. Let's review lesson 4. Federated learning by itself does not guarantee data privacy. Privacy-enhancing technologies, often referred to as PETs for short, like differential privacy and secure aggregation can help. Differential privacy, either central or local, works by clipping gradients and adding noise. Such privacy enhancements often come with costs like reduced utility and computational overhead.